This is 40 Days of Chemistry, part 20. This time we're looking at esters. And the first part of esters is to understand alkanols and alkanoic acids, the two chemicals that we use to react together to make esters. Now, alkanols have a functional group, the hydroxyl group. It can form hydrogen bonds, therefore they've got a relatively high melting point and boiling point because they are strong intermolecular bonds which require large amounts of energy to break. The names of alkanols need a locate number in front of the ol in the name if there's more than one isomer. So for example, methanol and ethanol only have one isomer, therefore you don't need a locate number. But propanol has two isomers, propan-1-ol and propan-2-ol, and therefore you do need to give that number before the ol in their names. There's some example pictures down there. Alkanoic acids have the carboxylic acid functional group, and you need to know this functional group. That's the carboxylic acid functional group. Sometimes you'll see it written as COOH, sometimes in its full structural form. Now this can form two hydrogen bonds per molecule, and therefore they've got higher melting points and boiling points, and more energy required to break the bonds and separate the molecules than the alkanols. Now, with alkanoic acids, you don't need locate numbers for the alkanoic acid if they've got one COOH group or one carboxylic acid group, because it's assumed to always be on the first carbon. So, for example, this is propanoic acid. You don't need a 1 in the name. However, things like citric acid with multiple carboxylic acid groups, then you do need the numbers in the name. But that's the only one that we know of in the U12 course is citric acid. A little thing not to forget about alkanoic acids, the carbon in the carboxylic acid group is part of the alkane chain. So this is actually 1, 2, 3 carbons, hence propanoic acid in that chain. Esterification reaction and esters basics. We know that alkanol plus alkanoic acid with a sulfuric acid, concentrated sulfuric acid catalyst, so I'm going to put conc here because it's concentrated sulfuric acid, is in equilibrium with an ester and water, and usually it's endothermic. And the important concepts to remember at esterification are it's an equilibrium reaction, but it's a slow reaction, and equilibrium lies to the left, and therefore we don't get very high yield of ester. It's usually endothermic, and it's a condensation reaction, therefore it produces this small molecule water. Now esters, the basics of esters are how to name them. Now you name the alkanol part first, and you change the ending from anol to il, and then you name the alkanoic acid part second, and you change the ending from anoic acid to anoate. So for example, pentan-1-ol plus ethanoic acid, you change it from pentan-1-ol to pentyl, and you change it from ethanoic acid to ethanoate, and the ester you produce is pentyl ethanoate. And don't forget that when you name them, you name the alkanol part first and the alkanoic acid bit second. The alkanol part only has one single bonded oxygen to it. The alkanoic acid part has the double bonded oxygen. Another way to remember it is you name it in according to the arrow. The ester makes it like an arrow shape with these oxygens here. You name it going from, in this case, right to left, but they could draw this ester in any orientation, so you need to be aware of how these two things react to make the ester. And please don't forget to put the water at the end. As a little bit of practice, there are 1, 2, 3, 4, 5 esters on the page here. It would be a good idea to name them mentally or write the names down, pause the video, do that, and then press play and check the answers. So here are the answers. This ester here is called ethyl propanoate. This one is called propylmethanoate. Here you've got methylbutanoate. Here you've got propylethanoate. And finally you've got propylpentanoate. Don't forget this carbon here is part of this chain, the pentanoate part of the molecule. The next thing we learned about was boiling points in this topic. We're comparing alkanoic acids, alkanols, and esters to also the alkanes, and there's three main trends you need to understand about these boiling points, particularly if you're comparing molecular weight versus boiling point, or number of carbons versus boiling point. First of all, it's the order. Alkanoic acids have higher boiling points than alkanols and esters than alkanes. The key idea here is the stronger the intermolecular bonding, the more energy is required to break the molecules apart, and therefore the higher the boiling point. Hence, alkanoic acids form 2 hydrogen bonds per molecule, have the highest boiling points. Alkanols with 1 hydrogen bond per molecule have the next highest boiling points. Esters are slightly polar. This ester group here with the oxygen sticking out the middle here gives that a slightly delta negative charge. And because it's slightly polar, they've got some dipole-dipole bonding. Therefore, esters' boiling points are below alkanols, but they're higher than alkanes because alkanes are non-polar. They only have weak dispersion bonding. The next trend you need to be aware is that as the molecular weight increases for all these types of compounds, the boiling point increases. And that's because as you increase the molecular weight, you're increasing the chain length. That means the molecules are longer and they've got more weak dispersion bonds, which means they've got stronger intermolecular bonding, and also they're heavier, which means they require more energy to vibrate, and that should be an R in there for vibrate. And that means the boiling point increases as the molecular weight increases. The third and final trend, and this is probably the minor one of these three trends, is as the molecular weight increases, the polar groups in the alkanoic acids, alkanols and esters makes up a smaller and smaller proportion of the molecule. They become more non-polar in effect, and therefore weak dispersion bonding becomes the main form of intermolecular bonding, and thus the difference in bonding points between these compounds starts to decrease as the molecular weight increases, as they become all more non-polar. But the key idea here, which I haven't written down, is that intermolecular bonding, the stronger the intermolecular bonding, the more energy is required to break the molecules apart, and therefore the higher the boiling points. And that moves on to uses of esters. So what are esters used for? Now, esters, as we said, have relatively low boiling points because they don't form hydrogen bonds. They just have some polar bonding or dipole-dipole bonding, which means they're volatile, but they have a pleasant odor, and that means as they're evaporating, that odor gets into the air, which we can smell, and therefore they're used for fragrances and flavorings in food. And examples of that, the two I use are octylethanoate, because the O and the E in octylethanoate is the O and the E in orange. That's used in orange scents. And butylbutanoate is used for pineapple scent. I don't know why I remember that one, but butylbutanoate is used as pineapple scent. Now, small chain esters is the second type of use. Small chain esters are polar and therefore used as solvents for polar organic molecules, for examples in glues, varnishes, and perfumes. And one common example is ethyl ethanoate. It's a widely produced solvent, and it's used as a solvent in nail polish remover, in perfume because it evaporates readily, leaving the scent of the perfume on the skin. It's used for decaffeinating coffee beans because the caffeine is soluble in ethyl ethanoate. And it's also used for cleaning circuit boards where using water would cause damage. So ethyl ethanoate is a very good polar solvent. That's on to the last thing now, is esterification, the practical details. And don't forget you need to be able to draw the esterification apparatus. We used a hot plate and a water bath. We have our reaction vessel here, a pear-shaped reaction vessel. We have a tube that goes from the pear-shaped reaction vessel up, so there's an open tube between the reaction vessel and the outside air. But around the outside of that tube is our condenser. The water goes in the bottom and out the top. That's so the condenser is completely filled and we get maximum heat extraction. And the key thing, the key phrase is refluxing is heating with a vertical condenser. You need to say both things. But why do we do refluxing? Well, the reason is the rate is slow for esterification and it's usually endothermic, and thus heating increases the rate because more particles of energy go to the activation energy and the yield of the esterification via the Chatelain's principle. But then the problem with heating is that ester being volatile evaporates at the high temperatures and would normally be lost. So heating under reflux condenses and returns the ester, allowing the higher temperatures and thus rate and yield to be obtained than would otherwise be possible if we weren't refluxing, because we just lose our ester. Another thing you might want to mention is the fact that we can't enclose the reaction because that would cause a pressure explosion, but the key idea is we can use higher temperatures than normal because by the refluxing process the ester condenses and is returned so we don't lose the ester. We also use a concentrated sulfuric acid as a catalyst. It's a catalyst because it provides an alternative reaction pathway with lower activation energy, so the rate increases, but also it's a dehydrating agent. It removes the water. So via the Chatelain's principle, equilibrium shifts to the right to produce more ester, and therefore increases the yield, which is unlike most catalysts, which don't affect the yield at all. So that's it for that particular focus area. We're moving on to electrochemistry next.